de su charla hoy es imaging of small penetrable objects based on higher order topological derivative. Su charla es como una continuación de trabajo de profesor André Novotny, que él habló en enero para nuestro departamento. Okay, Lucas, would you like to share the screen, please?
Yes. Just a minute. Let's try that. Okay.
And do you understand Spanish, right?
Yes, I can understand Spanish, but I can speak very well.
Because your father is from Argentina, right? That's like that, no? Yeah, can you listen to me?
Yes, yes,
okay.
I can.
Okay. So you can start now, please.
Okay. So first of all, I'd like to thank you, Javi, for the invitation and for giving me the opportunity to talk about one of our works. Professor Javi was my PhD thesis co-advisor. We've worked together since 2016, and we've had a scientific collaboration that works very well and a friendship that I appreciate a lot. So thank you again, Javi. Today, I'm going to talk about one of the inverse reconstruction problems that I studied at my PhD thesis. In this talk in particular, we focus on an inverse scattering problem for penetrable obstacles, which is modeled by a Helmholtz equation. And we've solved this kind of problem by using higher order topological derivatives. So I will show you how we obtain higher order topological derivatives and also how we use them to develop reconstruction algorithms for recovering small hidden obstacles. So in this inverse scattering problem, we consider omega as an open and bounded domain in R2 with a smooth boundary. We assume there may be an unknown number of disjoint hidden obstacles within the domain omega, and the union of all obstacles is denoted by omega asterisk. So there is a scalar field Z associated with the target domain, and this scalar field Z is solution for a boundary value problem governed by a Helmholtz equation with a Robin boundary condition like this one, okay? The parameter K omega asterisk is written as follows. Its value is gamma K in the region of the domain where I have an obstacle. Otherwise, in the remaining domain, its value is K. Okay? K and gamma are real positive constants. So in addition, we assume that we don't know this scalar field Z in all the domain omega, but just on its boundary. So in other words, we have partial information about the scalar field Z, okay? The main goal here is to reconstruct the set of obstacles, omega asterisk, okay? We want to reconstruct the set. So to deal with this problem, we assume that you know the nature of the obstacles, which means we know the value of gamma and K, but we don't know the shape and the location of the obstacles within the domain omega, okay? And we desire to reconstruct the topology of the obstacles with the help of measurements of this scalar field Z taken on the boundary of the domain. Okay, so physically, the scalar field Z is an incident acoustic wave field. So I have here the domain omega without obstacles, and a possible reconstruction to the set omega asterisk is this one. The exact reconstruction when the set small omega from the reconstructed domain coincides with the set omega asterisk from the target domain. So now I have a new scalar field U associated with the reconstruct domain. And this scalar field U is solution to a boundary value problem, very similar to the original one, except by the fact that the parameter K is now dependent on the set small omega that came from the reconstructed domain, right? So note that when the set small omega coincides with the set omega asterisk, we can conclude from the uniqueness of the solutions of the direct problems that the scalar fields U and Z coincides in all the domain omega and on its boundary in particular. So by assuming that we know the values of gamma and K, the unknown variable of our inverse scattering problem is the topology of the obstacles. So which allows us to rewrite the inverse problem as a topology optimization problem. So I introduce here the optimization problem, which is given by the minimization of the shape functional with respect to the set small omega. So again, if the set small omega is an accurate reconstruction to the set omega asterisk, then the value of the shape functional must be approximately equal to 0, okay? Because U is approximately equal to Z on the boundary of the domain. So now we have a topology optimization problem. A quite general approach to deal with this kind of problem is based on the topological derivative method. So I need to make a remark at this point. Here in these boundary value problems, the bold I denotes the imaginary number. So we are dealing with complex valued scalar fields, okay, U and Z. And this bar represents the complex conjugate of a function of interest. So since our methodology is based on the topological derivative concept, we start with an asymptotic expansion or the topologically perturbed shape functional like this one given in equation 1, okay, where the term dt psi represents the first order topological derivative. So, however, from the numerical point of view, we know that just the first order topological derivative doesn't provide enough information to achieve a good reconstruction of the obstacles. So we need more terms in this asymptotic expansion. So thus, in our methodology, we seek an asymptotic expansion of the topologically perturbed shape functional, like shown in equation 3, where the term dt psi is the first order topological derivative, and dt2 psi represents the second order topological derivative. So by using this kind of asymptotic expansion, written in terms of higher order topological derivatives, we are able to develop non-iterative reconstruction algorithms for solving the inverse problem. So here I have these two shape functionals. The shape functional psi of chi epsilon corresponds to the topologically perturbed domain, and the shape functional psi of chi corresponds to the unperturbed domain, okay? So when we are looking for the topological derivatives associated to the shape function of psi of chi epsilon, we need actually to write the difference between this functional in terms of a sum, where each term is a product between two functions. Okay, so one factor dependent on epsilon and another one independent on epsilon and dependent just on quantities corresponding to the unperturbed domain. Okay, so here in this term I have the same scheme, a function dependent on epsilon multiplied by another function independent on epsilon. So let's come back to the inverse problem. So note that the problem is stated in such a way that the reconstruction is conducted by using only one measurement associated with this function gr, okay? So I impose such a function, gr, on the boundary, and I use the respective solutions z and u to reconstruct the obstacles. However, the reconstruction can be performed from several measurements. So for this purpose, it's enough to impose different functions gr as raw bin data. So for each function gr, I collect the respective solutions z and u, and then, in this way, I have much more information to reconstruct the set of the obstacle. So from now on, I consider this shape functional, okay, for several measurements. So in addition, each circular or non-circular obstacle is to be reconstructed as a ball-shaped geometry, right? So the solution of the inverse problem can be expressed by two vectors. One of them carries the centers, while the others carries the radii of the ball-shaped geometries, okay? Well, now I'm going to start a very technical part of this lecture where I show you how we obtain an asymptotic expansion of the shape functional j omega in terms of higher order topological derivatives. So we first define these two functionals, j epsilon and jo. We define the shape functional jo as given in 5, and it depends on the scalar field uo, which is solution to the boundary value problem 6, okay? Note that the parameter k here is fixed, okay, because you have chosen the empty set as an initial guess to the set small omega. Okay, so in other words, Jo is the shape functional associated with the unperturbed domain. Okay, this domain here is then perturbed by a finite number of small circulations, small circular inclusions. So I have the topologically perturbed shape functional given by expression 7, and it depends on the scalar field u epsilon. And this scalar field u epsilon is solution to the boundary value problem 8. So in this boundary value problem, the parameter k epsilon is writing as follows. Its value is gamma k in the region of the domain where I have a small circular perturbation, and in the remaining domain, its value is k. So now I have an explicit form for these two functionals, j epsilon and jo, and I can evaluate the difference between them. So after doing some algebraic manipulations, I find expression 9. So since I'm looking for an asymptotic expansion with respect to epsilon, I need to manipulate the scalar field u epsilon, because this is the function, this is the only quantity here carrying the small parameter epsilon, right? And note that we are not able to solve problem 8, the boundary value problem 8, analytically, because it's written in terms of a general referencing domain omega. Okay, so I propose the following asymptotic expansion with respect to epsilon for the scalar field u epsilon as given in 10. I have new elements here that need to be clarified. So first of all, I wrote an expansion in terms of alpha I. Okay, alpha I carries the small parameter epsilon. Okay, alpha I is equal to pi epsilon I squared. So in other words, alpha I is the area of a circular inclusion whose center is at xy and its radius is epsilon y. Beta is a quantity dependent on the contrast gamma, And the simple sum is here introduced because you are considering a finite number of circular perturbations. Okay, and the double sum is needed because it's relevant for us to capture the influence from a perturbation in another one. Okay. In addition, in 10, we have U epsilon and UO. They are solution to boundary value problems that we already know. And these new functions, hi epsilon, hij epsilon, and U epsilon tilde, are solutions to boundary value problems as well. So let's know such problems. So in particular, the red function hi epsilon is solution to the boundary value problem 11. Okay. The goal here is to know the behavior of this function hi with respect to epsilon. So I will manipulate problem 11, rewrite such a problem to do that, to achieve my goal. Okay. So in problem 11, I have this non-trivial source term written as a fraction, and I sum and subtract UO of xy in the numerator of this fraction, and I decompose the function hi epsilon as a sum of three functions, pi epsilon, qi, and hi epsilon tilde, as given in 12, right? Okay, the function pi epsilon is solution to problem 13, which admits an explicit solution written in terms of Bessel functions. So here are the Bessel functions. Okay, so why were you able to solve problem 13? Okay, because we have put the topologically perturbed domain inside a ball BR. So by doing this, we could solve problem 13 by using polar coordinates, okay? Note that we have a solution for the case when x belongs to the b epsilon I ball, and another solution when x is outside this ball. So here I have lambda 1, lambda 2, and lambda 3, okay? They are real constants dependent on epsilon, as shown in these expressions here, 15, 17, 15, 16, and 18. Okay, and such constants admit a series expansion at epsilon equals to 0. So we will use this series representation in further calculations, right? Okay, next, the function qi is solution to the boundary value problem 19, which is constructed in order to compensate the discrepancies introduced by the function pi epsilon on the boundary of the domain omega. So this function does not depend on epsilon, okay? And the problem itself is numerically solved in our algorithm. The function hi epsilon tilde solves problem 12, and this function does not appear in the closed form of the topological derivative. So I mean, it appears just in the remaining terms of the asymptotic expansion of the perturbed shape functional. So we don't use it in the development of our algorithm. Okay, we still have two functions here, hij epsilon, firstly, and this function is solution to the boundary value problem 21, whose governing partial differential equation is not simple due to its source term. However, we don't need to solve such a problem because in further calculations, we replace the function hij epsilon by the adjoint state v, which is obtained as a solution to the problem 24. Okay, and finally, we also have the function u epsilon tilde, a solution to the problem 22, and such a function does not contribute to the closed form of the topological derivatives. So we don't have to worry about this problem. Okay, now we know all the elements present in the asymptotic expansion of the scalar field U epsilon, given by 26. And we also have the difference between the functionals given by 25. So then I subtract UO from both sides of equation 26. And now I can replace 26 into 25, and I obtain the expression 27. Okay. Okay, let's recall our goal here. I'm looking for an asymptotic expansion like this one in equation 29. And as I manipulate equation 25, remaining terms came naturally in this process. Okay, so at each step of our calculations, we are perhaps generating more and more remaining terms. However, they aren't important because you don't use them to devise the algorithm. So in this work in particular, we consider as remaining terms those that are multiplied by alpha raised to a power greater than 2. Okay, so such remaining terms are highlighted in Greek color, and I will not show you them explicitly. Okay, obviously, this expansion, asymptotic expansion 28, is not the final form of the asymptotic expansion because we have these functions hi epsilon, hij epsilon, that obviously are dependent on epsilon. So we'll have more work to do here. Okay, here I'm going to work in this first integral. We will replace it by another simpler integral by using the weak formulation for the problems corresponding to the scalar fields V and hi epsilon. So in 30, I have the weak formulation associated with the problem corresponding to adjoint state V. And in 31, I have the weak formulation associated with the problem corresponding to the scalar field hi epsilon. Okay, in 30, I take eta equal to hi epsilon, and in 31, I take eta equal to V. And then I obtain the equalities 32 and 33, respectively. And now I take the real part on both sides of this equation. So since the left-hand side of 32 is equal to the left-hand side of 33, we can conclude that the right-hand sides of these equations are equal. Okay, and then we can replace this integral here by this expression in 34. Okay, right. By following an analogous procedure, we can replace this integral by this expression in 35. So the advantage here lies in the fact that I don't need to work with this function 8ij epsilon that comes from a difficult boundary value problem to be solved. Instead, I can deal with the simpler function hj epsilon and v. Okay, so as you can see, so after replacing this expression in this integral here, I obtain 36. And as you can see in 36, this is not the final form of the asymptotic expansion yet. We still have some work to do because you have integrals defined in the b epsilon eyeball, and we have functions dependent on epsilon, right? This function too. So we have some work to do. Now we work in this term, highlighted in red color, and we split this term, this double sum, in the case when I is equal to j, okay, and we obtain this term, and you also consider the case when I is not equal to j, and I obtain this term here. So splitting that sum like I did is very relevant in this case, because I recall you that the function hi epsilon was decomposed in this format, and the function pi epsilon has a representation inside the b epsilon I ball and another representation outside the ball. We use this information in 39, okay? So here the function hi epsilon is defined for the b epsilon I ball, and the domain of integration is also the b epsilon I ball. So in this case, we use the representation in red color, okay? And now I have this function hj epsilon, which is defined for the b epsilon j ball, and the domain of integration is the b epsilon I ball. So these are different balls, and you must use the representation in blue color, okay? And finally, in this last integral, I have the function hi epsilon, which is defined for the b epsilon I ball, and hj epsilon, which is defined for the b epsilon j ball. And the domain of integration is the boundary of the domain. So in this case, I will use the blue color representation of the function hi epsilon, okay? So by doing the corresponding replacements, we obtain expression 42, right? We still have some work to do because we have integrals whose domain of integrations are the b epsilon I ball. So we have a lot of integrals here. And we also have these constants dependent on epsilon, okay? But I promise you this is the last step in our calculations. So I have different functions in these integrands, okay, uo, v, qi, pj, epsilon. And since the domain of integration is the b epsilon I ball for all integrals here, we will consider the Taylor's expansion of these functions that I mentioned before. And in addition, I also consider the series expansions of the constants, lambda 1, lambda 2, and lambda 3. So after considering all these procedures, I'm able to solve those integrals, and I obtain the final form for the asymptotic expansion of the perturbed shape function, okay? So here in equation 44. So note that we obtained an asymptotic expansion with respect to alpha. So we have one term multiplied by alpha. So this term can be interpreted as our first order topological derivative. We also have one term multiplied by alpha squared log alpha, and this term can be considered as our second order topological derivatives. And we have a lot of terms multiplied by alpha squared. The sum of all these terms can be considered as our third order topological derivatives. And all the remaining terms are denoted by this little o of alpha squared. Okay, So next, we use this asymptotic expansion to devise the reconstruction algorithm. So as I told you earlier, we must disregard all the remaining terms, okay? So we not consider the remaining terms to develop the algorithm. In the asymptotic expansion without the remaining terms is denoted by delta J. So note that the right-hand side of equation 45 is dependent on the number of obstacles, okay, the center of them, which is represented by the Greek letter psi here, and the size of the obstacles, okay, which is denoted by alpha, okay, and here I have alpha also. So for computational purposes, we rewrite equation 45 in a matrix format, which is given by 46, where D is a vector and capital G and H are matrices whose entries are given below. So again, D can be interpreted as the first order topological derivative, G is the second order topological derivative, and the matrix 8 is the third order topological derivative. So we are dealing with a topology optimization problem, which is in fact a minimization problem here. And expression 47 is a quadratic form with respect to alpha. Then we proceed by differentiating expression 47 with respect to alpha and making the resulting expression equals to 0, which leads us to the nonlinear system given by expression 49. So we solve this nonlinear system of equations using the Newton's method, and the quantity alpha solution of 49 becomes a function dependent on the centers psi of the obstacle. So in other words, we solve equation 49 for a specific point of the domain omega, right? So next we replace the solution of 49 into expression 47, and we obtain the expression between braces in 50. So we find the optimal location of the obstacles denoted by psi star by solving this minimization problem, which requires a combinatorial and exhaustive search over all the points pertaining to the set of admissible locations, capital X, okay? And finally, the optimal size of the obstacle, we denoted by alpha star, is simply the alpha corresponding to the optimal location psi star, okay? There is a simpler version of the previous algorithm. Let's suppose the second order topological derivative is not relevant in the reconstruction process. So we disregard the matrix G from equation 51, which allows us to compute the quantity alpha from the linear equation 53. So as you can see, we have two very similar algorithms. In the first one, the quantity alpha is obtained from a nonlinear system of equations, and you solve it by using Newton's method. And here, we can obtain alpha by solving a system of linear equations, so which requires just the inversion of the matrix H. So it's much simpler, okay? I'd like to explain better how the algorithm works, okay? More precisely, let's understand why the reconstruction of the hidden obstacles is performed through a combinatorial and exhaustive search over a set of nodes extracted from the original mesh. So first of all, some of the inputs are the topological derivatives themselves, okay? And they are written in terms of scalar fields. So UO, V, QI, which in turn are solutions to boundary value problems, okay? So the reference domain is a circle, a unit disk centered at the origin, and the circle is discretized in finite elements, and all the boundary value problems are solved over this very fine mesh, okay? So we are able to know the value of the topological derivatives, D, G, and H, at each node of this blue mesh, at each node, okay? So if there is a hidden obstacle within the reference domain, then its center must be located at a node of the blue mesh, okay? However, as you can see, this is a very fine mesh, and there are thousands of nodes here, okay? So it's infeasible to look for the location of the obstacles considering a search space with so many possibilities. So instead, we consider a much smaller search space, say with only nodes uniformly distributed within the reference domain omega, and such a set of 9 nodes is denoted by X, okay? So this is the set X of admissible locations for the obstacles. So I'm considering so few nodes because I want to show you a particular example, a fictitious example, right? So the inputs are the topological derivatives, the number of obstacles to be reconstructed, the number of nodes in the set X, and the number of measurements. So for a specific node in the set X, capital Pi denotes the mapping from the nodal index to the corresponding nodal coordinates. So psi assigns the nodal coordinates of a specific node from the set X. So once we have the nodal coordinates, we can compute the value of alpha. Thus, for each node from the set X, we obtain a pair, okay, psi and alpha of psi. And the pair psi alpha that minimizes the quantity S is the optimal solution to the optimization problem. So let's suppose there is a hidden obstacle located at the origin. In order to reconstruct the obstacle, we are going to perform an exhaustive search over all the nodes of the set X, okay? Here, the reconstruction process is performed from the linear algorithm. I mean, we are using just the topological derivatives D and H, okay? So we start with the node I1. So you compute the value of the topological derivatives corresponding to this node I1, and you use them to calculate the value of alpha and S. So let's suppose the quantity S is less than S star. So then the pair psi alpha is a candidate point to the global minimum. So note that the first node, I1, is always a candidate point to the global minimum because we have initialized S star with infinity, okay? So we go to the next node, I2. We compute the topological derivatives corresponding to I2. Next, we calculate the value of alpha and S, and you verify if the pair psi alpha is a candidate point to the global minimum. Let's say yes, okay? So the new value, S, is less than the value of S corresponding to the node I1, and then the node I2 is the new candidate point to the global minimum. So this process is repeated to the nodes I3 and I4. Maybe these nodes are new candidate points to the global minimum, maybe not. Let's suppose no in this example. And of course, the node I5 is expected to be the global minimum point because the obstacle is in fact located at this node. So, however, we are not sure about it at this moment, okay? We must consider the next nodes because we are dealing with an exhaustive search over all the nodes over the set X. So if our methodology and the algorithm itself work well, then the nodes I6, I7, I8, and I9 are not new candidate points to the global minimum, and the optimal solution stores the value of S, alpha, and Xi corresponding to the node I5. Okay, so the reconstruction of multiple obstacles is more complicated, and it requires a combinatorial and exhaustive search over all the nodes over the set X. So for example, if I try to recover two obstacles with a set X containing 9 nodes, then I must take into account the combination of all the 9 nodes, taking 2 at a time. So it gives us 36 attempts to finding the global minimum point. Okay, let's start the numerical examples. We are going to the final part of the lecture. I consider the recursive domain as a unit disk centered at the origin. The blue mesh and the set X are constructed accordingly to each example. And we consider this complex exponential function gr as Robin boundary data. Okay, so note that for each angle theta here, gr is a different function to be imposed as a boundary. Okay, in this first example, we investigate the sensitivity of the reconstruction with respect to the size of the subgrid. So here we want to reconstruct a single obstacle from the nonlinear reconstruction algorithm with only one measurement. Okay, the red and black circles represent the predicted solution and the target, respectively. So for this first subgrid, none of its interior nodes coincides with the center of the target obstacle. So in this case, the algorithm returns a location, a node which is closest to the real center of the inclusion. So for the second subgrid, despite such a subgrid is more refined, again, none of its interior nodes coincides with the center of the target obstacle. In this case, the algorithm keeps returning a location, a node, which is closest to the real center of the obstacle. So finally, this last subgrid X contains a node which coincides, okay, with the center of the target obstacle. So in this case, the algorithm is able to return the exact solution, the exact location of the obstacle. So in addition, we highlight that the size of the target obstacle was accurately predicted in all cases. Well, in this example, we analyze the influence of the number of measurements in the reconstruction of two obstacles of different sizes. So the results are obtained from the nonlinear reconstruction algorithm, and the target domain is this one, shown in figure A. So firstly, the reconstruction is performed by using only one measurement, okay, in the case when the angle theta is equal to 0. As you can see, we failed in reconstructing both obstacles. Their sizes were not accurately predicted, and their centers don't match the true ones. So such a result does not show any improvement when the reconstruction process is performed with 2 or 3 measurements simultaneously. However, when the reconstruction process takes into account 4 measurements, the algorithm successfully recovers the 2 obstacles. So this example shows us that for multiple obstacles of different size, more information is required to achieve an accurately reconstruction of the target domain. So you need more measurements, okay? Okay, here we test the linear reconstruction algorithm. to predict multiple obstacles, okay, of the same size. So the results are obtained from 3 measurements. And we have, in this case 1, we have 3 obstacles quite apart from each other, okay? Here is the result from the nonlinear reconstruction algorithm, and here is the result from the linear algorithm. So the case 2 considers 2 obstacles of same size, but they are very close to each other. And here is the result from the nonlinear and linear reconstruction algorithms respectively. And this example 3 shows us that 1, the reconstruction algorithms accurately reconstruct the hidden obstacles, and there is no difference between the predicted results. And 2, the second order topological derivative, represented by the G matrix, does not have a strong influence in the reconstruction process. So we can, in fact, disregard such a term and proceed with the linear algorithm in the forthcoming examples. Okay, in this example, we analyze the sensitivity of the reconstruction with respect to noise data. Okay, so we add noise to the system by replacing the parameter k omega asterisk by this expression in red color. Okay, where tau is a random variable taking real values in the interval from -1 to 1, and mu corresponds to the level of noise. So since we are going to reconstruct 3 obstacles of same size, we conduct the numerical experiment by taking into account the same 3 bound robin data used in the previous example. So in the first round of the experiment, the level of noise is 30%, and the algorithm successfully reconstructed the center in radius of each obstacle. Now the level of noise is 50%, and the result is quite good. And for more noise input, the reconstruction result loses accuracy, and the centers of the predicted obstacles don't match the true ones. Okay, so we have good results up to 50% of noise in the target domain. So in this example is very interesting. In this example, we reconstructed an L-shaped geometry, L-shaped obstacle, and a triangular one from 3 measurements here. 3 measurements by using 2 ball-shaped inclusions, okay? So in this case, the predicted centers are very close to the centroids of the target obstacles, and the areas occupied by the circular inclusions are approximately equal to the areas of the non-circular obstacles. So these results are obtained for levels of noise up to 50% again, and for more noise input, the accuracy of the result is reduced, and the effectiveness of the proposed algorithm is not ensured. And here I have a last example. We reconstruct 5 obstacles of same size from partial boundary measurements. It means we collect information about the domain in these 4 parts of the boundary, okay, represented by thick black lines here. The results are obtained from 2 measurements, so it's very, very good. We can recover 5 obstacles by using just 2 measurements. And in all the results that I will show you, the level of noise is 35% here. So this first result shows that the algorithm successfully reconstruct all the 5 obstacles from partial boundary measurements. And as the size of the border observation region becomes shorter and shorter, the reconstruction results tended to be more degraded. Of course, because I have less information to recover the obstacles, okay? Okay, in the conclusions, I have here some general remarks about the reconstruction algorithms we have developed. First, the algorithms are able to reconstruct multiple obstacles in a non-iterative scheme. So, however, the price I pay for that is the associated computational cost, which is quite high due to the fact that we need to conduct a combinatorial and exhaustive search in order to find the optimal location of the obstacles. So here is an advantage, pro, and in addition, the algorithms are independent of any initial guess, it's another pro, and these first two pros make the algorithm very robust with respect to noise data. Okay, so we can work with the level of noise up to 50%, you have good results, right? So on the other hand, the set of obstacles is reconstructed by ball-shaped geometries, which can be seen as a limitation of our approach, since you have some difficulties in recovering the shape of a more complex obstacle. So this is a con, and the high computational cost due to the exhaustive combinatorial search is also a con of our algorithm. But despite these mentioned cons, we believe our method can be used for supplying a good initial guess for more complex iterative approaches, such as the ones based on level set methods, right? So I think that's all. Thank you for your attention. Javi?
Thank you, Lucas. Thank you. I like the talk. It was nice. Sí, si alguien tiene duda, pregunta, comentario, algo.
Nice talk. Thank you, Lucas. So
Thank
I
you.
just want to know this model for the scattering problem. There must have been some earlier work on using topological derivative. How is it different, and what is the novelty? And can you?
Repeat, please. What
No,
is the...
I mean to say, are there previous work on the same problem using topological derivative? And what is new in this thing? Meaning, what is meaning? I don't know if I'm able to explain myself.
I think the main difference is in the it's about the obstacles themselves, because here we are considering penetrable obstacles. So and you have a new boundary condition to consider as well. So when I consider penetrable obstacles, I need to model it properly. So we have transmission conditions in the boundary value problem. And also, we are considering the Robin boundary condition in the boundary value problem. So it changes the asymptotic analysis, and it changes also the computational, the numerical computation of the boundary value problems.
Thank you.
Yeah. Okay.
¿Alguien más? ¿Más preguntas, más comentarios? Okay, and so Lucas, I would like to make three comments very quickly for Rajesh to understand better. Okay, there are 3 points for the pure mathematician, for the applied mathematician, and for the engineers. For the pure mathematician, the point to be noted that Lucas is calling it second order derivative, right? Again and again. But if you observe, the order is not 2, order is alpha log alpha. And why it is that? Because the problem is of dimension 2. If you do the same analysis for dimension 3, it will be alpha square. So in general dimension more than 2, it will be alpha square, alpha cube, and in dimension 2, it's alpha and then alpha log alpha. So it's not like exactly 2, but we are calling it 2. Lucas was calling it order 2. Number
Yes.
one, this is for the pure mathematician. For the applied people, it can be observed that the algorithm is working with the noise, right? But the
Yes.
analysis is not done. Analysis is not done with the noise. Analysis is done for a deterministic problem, right? But somehow with the noise, even if we forget the analysis, algorithm is working. Okay. Number 3, for the engineers, if we observe that just in the slide which is here, example 5, even the unknown obstacle is of L shape or triangular or any other shape, up to some level we can get the volume. So if you can imagine the concept of detecting cancer, or maybe the oil source in the water bed, in the seabed, we can exactly get the how much oil or how big the cancer is. We may not get exact shape of the cancer or the oil, but we can get similar or approximate how it looks. So these 3 points, maybe Lucas forgot to mention. These were important.
Yeah, I
And
think
that's
you
all.
summed it very well.
Yeah. So these are the only thing I wanted to mention. If anybody else wants to comment something, please.
Perfect. Yeah.
See, no,
Can you not
yeah, Rajesh,
can
please.
you not obtain the shape also by approximating the shape by several circular like pieces? No.
No. Only L will be approximated by one circle, but the volume will be approximately same as L.
Yes.
Yeah. Yeah.
Yeah. In this
Okay.
case, unfortunately, we are not able to recover. For example, let's suppose that in this case, let's suppose you have an example where the L-shaped obstacle is in the center of the reference domain, okay? Okay, so a question is the following. Maybe we can recover this this non-circular geometry by, I don't know, let's suppose 3 balls like this. Oh, sorry. 3 balls like this. Lit. So we tried to do that, but we were not successfully in the reconstruction. In fact, what happens is what Javi said. We just are able to recover non-circular obstacles by circular obstacle, but one to one.
Yeah, but Lucas, there is a huge difficulty mathematically here. What Rajesh is saying. In this problem, the hypothesis is that the balls are not intersecting, right? Theoretically. So balls are well separated, and this thing, and if the balls are well separated, you cannot approximate any shape by using balls. But because if you want to use the balls to approximate any shape, these balls must cut each other. What we see in the analysis course, that by Lindelof theorem, something like that.
Yeah, you're totally right. This is the best explanation for explain why this kind of reconstruction doesn't happen in our case. Doesn't happen.
Exactly. That's nice. Okay. Entonces, paramos acá. See? Thank you, Lucas, once again. Thank you very much for the talk.
Okay. Thank you, Javi. See you.
See you. Bye.
Bye.
Chao.
Bye bye.
Nos vemos próximo jueves.